Hi guys, and welcome back to section 2, where we are going to talk about the scripting power of Python. So why scripting? Well, often you may find yourself undertaking tasks that involve many repetitive operations. To combat this repetition of work, it may be possible to write a macro to automate those operations within a single application. But if in the operation span several applications, macros are rarely effective. For example, if you back up and archive a large multimedia web application, you may have to deal with content produced by one or more media tools, code from an IDE, and probably some database files too. Instead of macros, you need an external programming tool to drive each application or utility to perform its part of the whole. Python is well suited to this kind of orchestration role. So what is scripting? Scripting is a term that means different things to different people, so it's important to clarify upfront what it means when you see it in this lesson. It means coordinating the actions of other programs or applications to perform a task such as bulk file printing or an automated workflow, or adding a new user. You could be using operating system utilities or large general purpose packages like an Office productivity suite. Think of the way that a script in a play tells the actors what to say, where to stand, and when to enter or exit the stage. That's what Python scripting does. It coordinates the behavior of other programs. So in this lesson, we'll learn how to use Python modules to check user settings as well as directory and file access levels. We set up the correct environment for an operation and launch and control external programs from our script. We will also discover how Python modules help us access data in common file formats, how to handle dates and times, and finally how to directly access the low-level programming interfaces of external applications using the very powerful C-types module, and for Windows the PyWin32 package. So there are system-specific issues here. So by nature of this lesson, much of this section's content is operating system specific. Some modules try to be portable across operating systems, whereas others support only a subset of operations on some systems. Others come with dedicated modules that work only on that platform. So when I show you the example here and you find an example that doesn't seem to work for you, make sure it is not for a different operating system. So I'll try to distinguish between the different operating systems underway. So whenever possible, we try to point this out, as I said. Also, if you're following along, the output is often quite specific to the user and operating system, so don't expect to get exactly the same result as shown on my screen. For example, when checking user details, you should see your own username and not one shown on my screen. So the first lesson we are going to talk about is accessing the operating system. So most of the tasks that a typical programmer needs to undertake using the operating system, for example, collecting user information or navigating the file system, can be done in a generic way using Python's standard library of modules. So recall that modules are reusable pieces of code that can be shared across multiple programs. The key modules have been written in such a way that the peculiarities of individual operating system behaviors have been hidden behind a higher level set of objects and operations. The modules that we consider in this section are OS path, OS/path, PWD, glob or glob or glob, I'm not sure how you pronounce it, shuttle, and subprocess. So material here focuses on how to use these modules in common scenarios. It does not try to cover every possible permutation or available option. The OS module, as the name suggests, provides access to many operating system features. It is in fact a package with a submodule, os.path, that deals with managing file paths, names, and types. The OS module is supported by a number of other modules that we meet as we work through the various topics in these lessons. This myriad of modules are collectively referred to as OS modules, uppercase, and the actual OS module as OS lowercase. So if you are familiar with systems programming on a Unix system, or even with using a Unix shell as bash, many of these operations will be familiar to you. The OS is primarily here to manage access to the computer's hardware in the form of CPU, memory, storage, and networking. It regulates access to these resources and manages the creation, scheduling, and removal of processes. The OS module functions provide insight and control over these OS activities. So in the next section, we are going to look at the common tasks of collecting user and system information, managing processes, determining file information, manipulating files, navigating folders. And note that one of the biggest changes in Python version 3, its increased focus on internalization and recognition and use of Unicode. The OS module is no exception, and the function accepts Unicode strings. However, the underlying OS functions and file names are not necessarily Unicode aware, and Python will in those cases do a conversion to bytes using the system encoding found in sys.getFileSystemEncoding function. This is not guaranteed to work in every case, so very occasionally a Unicode error may be raised. In those cases, you either have to convert the string into a more OS-friendly form before calling the function, or look for an alternative approach to solving the problem. So now let's try to work with these modules. We will now start to obtain information about users and their computer. So one of the first things we can do is to explore the OS modules and find out what they can tell us about the users. Specifically, we can find the user's ID, login name, and some of his default settings. So we'll work in the Python interpreter. I'll just clear the screen. And try to be in the working directory that you have all the codes in, because we will create some folders. So we can start to type the following codes in the interpreter. Sorry, we have to be in the interpreter first. Import OS. Now we can try to get login info. It's the login info. So if you are on a Mac, you can use this function. I will tell you what it is later. And also, if you are on Mac, you can import pwd. It won't work on Windows. This will also not work on Windows, so if you're on a Mac, you can try that. It will work for you. Okay. Yeah, of course, it won't work on Windows and PWD, but it'll work on any Unix-based system. So just try out this function if you're on Mac. So after importing the OS module in the first line, we got the login name as a string. This is generally most useful for creating personalized prompts or screen messages. Unfortunately for Windows user, that's it. The rest of it, the code that we tried, it's suitable for Unix-based systems only. However, all is not lost, because you can also find some of this information from environment variables, which we look at a little later. So if you have a Unix-based system, you use the os.getUID to get the user ID as the OS sees it, namely a numeric value, which you can then use with various other functions. The next line, import and use function from the password module pwd to translate the OS user ID into a more complete set of information that includes the real name, default shell, and home directory. As I said, this is for Unix-based systems. This is obviously much more informative, but it requires the UID from os.getUID as a starting point. An alternative function, os.getPWNAM, takes the login name instead and returns the same information. Finally, we use the pwd.getPwall and a for loop to extract all of the usernames for this system. Of course, this will work on Unix-based systems. So the next, we find out what kind of permissions the user have on files they create. This is significant because it affects any files our code produces. It may be that we need to temporarily alter the permissions. For example, if we need to create a file that we execute later in the program, it needs to have execute privileges. In Unix, these settings are stored in something known as unmask or user mask. It is a bit mask, like the ones we discussed earlier, where each bit represents a user access data point as described next. Python lets us look at the umask value even on Windows using the os.umask function. The os.umask function has a slight quirk in its usage. However, it expects us to pass a new value to the function. It then sets that value and returns the old value. But if we only want to find out the current value, we can't do it. Instead, we need to set the umask to a temporary new value, read the old one, and then reset the value to the original. The format of the mask is very compact, consisting of 3 groups of 3 bits, 1 group for each of owner group and world permissions respectively. So note, 3 bits can be concisely shown as an octal digit, and for that reason we often find Unix documentation that expresses these values in octal. Python can use octal values too, by representing the numbers with 00 in front, so that 0077 represent 9 bits, all set to 1. So let's just try to work with the umask functions. So again, in the Python interpreter, import OS. We have already done that, so I'm not going to do that again in case you quit and restarted it for some reason. So we have just used the umask to play with the bits values of, for example, a file name, and converting the bit values. So sometimes we want to know what kind of computer system the user is running, in particular the details of the OS itself. Python has several ways of doing this, but the one we'll look at first is the os.name property. So at the current time, the property returns one of the following values: POSIX, NT, Mac, OS2, CE, or Java. The Java value is included, although not strictly an OS, for Java versions of Python as opposed to the default C version. It is useful to know that you are running under a Java virtual machine, also called a JVM. Another place to look for the system the user is running is the sys module, SYS, and in particular the sys.platform attribute. This attribute often returns slightly different information than that found using os.name. For example, Windows is reported as Win32 rather than NT or CE. On Unix, another function in OS called os.uname provides slightly more detail. So if you have several different OSs available to you, it can be interesting to compare the results from these different techniques. It is recommended that you use the os.name option simply because it is universally available and returns a well-defined set of results. One other snippet of information that is often useful to collect is the size of the user's terminal in terms of its lines and columns. We can use this information to modify the display of messages from our scripts. The shuttle module provides a function for this called shuttle.get_terminal_size, and we'll use it in just a second. Let's go into Python again. So if the terminal size cannot be ascertained, the default return value is 80 by 24. A different default can be specified as an optional argument, but 80 by 24 is usually a sensible option because it's the traditional size of the terminal emulators. Mine is a little bit different. And next I want to talk about is obtaining information about the current process. This is very useful for if you are sysadmin, and it can be useful for a program to know something about its current status and runtime environment. For example, you might want to know the process identity, or if the process has a preferred folder in which to write its data files or read configuration data. The OS modules provide functions for determining these values. One such source of process information is the process environment, as defined by environment variables. The OS module provides a dictionary called os.environ that holds all the environment variables for the current process. One thing to note is the number of variables on any given system depends on all sorts of local considerations, including the number and nature of the applications installed, because many applications create their own environment values during installation. So the disadvantage of environment variables is that they are highly volatile. Users can create them and remove them. Applications can do likewise. So it is dangerous to rely on the existence of an environment variable. We should always have a default value that we can fall back on. Fortunately, some values are fairly reliable and usually present. 3 of these are particularly useful for Windows user because the pw.get pwuid and os.uname functions that we talked about earlier are not available. These are home, OS, and processor underscore architecture. So if we do try to access a variable that is not defined, we get the usual Python dictionary key error. On most, but not all operating systems, a program can set or modify environment variables. If this feature is supported for your OS, then Python reflects any changes to the os.environ dictionary back into the OS environment. In addition to using environment variables as a source of user information, it is quite common to use them to define user-specific configuration details about a program. For example, the location of a database. This practice is slightly frowned upon nowadays, and it's considered better to use a configuration file for such details. But if you are working with older applications, you may need to refer to the environment for such things. So let's try to investigate the process environment on my computer. You can do on yours. I will explain a little bit later what I'm. This will work for Mac users. Like I said, I will explain in a minute. So after importing the OS in the first line, the first thing we did was determine the current process ID. We are in the Python interpreter, so it is the interpreter process itself that we are identifying. The next line reads the parent process ID. In this case, that is the OS shell program. We can use these IDs when interacting with other operating system tools as described in the next section. We then use the os.getCwd function, which stands for get current working directory, to determine which directory is currently the default. This is usually the directory from which the interpreter was invoked, but as you will see, it is possible to change directory within our program. os.getCwd is a useful way of checking exactly where your code is working at any given time. Next, we find out how big our environment was by displaying the length of the os.environ dictionary. We then pulled out the values of the home. Try to do that. Home environment variable that shows the user's home directory. This will work for the Unix command. We then tried to access a variable called testing123, but because it did not exist, we got the key error. We attempted to create a testing123 variable by assigning the number 42, but that yielded a type error because environment variables must be strings. We then assigned the string value to 42 as a string to the testing123 variable and has succeeded in creating a new environment variable for this process. Remember that the environment is local to this process and any sub-processes that it spawns. This is not visible to other external processes. And next, in the code example, we read the value again, and this time got a value with no error messages, confirming that we had succeeded. Finally, we deleted the variable and proved that it was gone by once more attempting to read it, resulting in, as expected, an error. So the next section I'm going to talk about is managing other programs, and it is useful to be able to run other programs from within a script. And the subprocess module is the preferred tool for this. The subprocess module contains a class called popen that provides a very powerful and flexible interface to external programs. The module also has several convenience functions that we can use when a simpler approach is preferred. The documentation describes how to use all of these features, so please check out the documentation. So in this section, we only use the simplest function subprocess.call and the popen class. One note, historically, Python has had several ways to run subprocesses. This has led to considerable confusion and a proliferation of options. Most of these mechanisms are still available so as not to break old code, but you are strongly advised to use the subprocess module discussed here for any new code you write. The most basic use of the subprocess module is to call an external OS command and simply allow it to run its course. The output is usually displayed on screen or stored in a data file somewhere. After the program completes, you can ask the user to make some kind of selection based on what was displayed, or you can access the data file directly from your code. You can force many OS tools, especially on Unix-based systems, into producing a data file as output by providing suitable command line options or by using OS file redirection. This technique is a very powerful way to harness the power of OS utilities in a way that Python can use for further processing. This basic mechanism for calling a program It's wrapped up in the subprocess call function. And this function has a list of strings as its first parameter, followed by several optional keyword parameters that are used to control the input and output locations and a few other things. So let's try to work with the subprocess module. I'll just go back to clearing the screen. So you can either create a test directory called root, it's up to you, and populate it with a few text files. Either you can create them from scratch or copy them from somewhere else. It doesn't matter what they contain. We are only interested in their being there at this stage. So to get the same result as I'm going to show, so I'm just going to create some this is my root directory, so I'm just going to create a couple of files here. I did not mean to open the file. Just want to rename it. So just 2 files. Then we import the subprocess module. And for Mac and Linux based users, you can use this command to list all the contents of your current folder. And Windows users can do the following. It's a little bit long and messy to write. Excuse me. So this command gives us all the files that are in our current working directory. So after importing subprocess with the alias sub in the first line, it just saves some typing later to call it alias as sub. And we call the sub.call for the first time with the argument with the cmd/c dir/b for Windows. And the first line I'll explain in a minute. So the second line, this one that listed all the files, notice that there is actually a subcommand of the cmd.exe shell process. The Windows help system explain what the /c and the b flags do. The output is displayed on the stdout, our terminal, but the file names are not accessible from within Python. The only thing returned by call is the operating system return code, which tells us if the program completed successfully or not, but it does not help us to interact with the data in any way. So we then use the subcall a second time, but this time we redirected the std out to a new file, ls.txt. That's what happened here. Yep, there. And the next, we use the operating system tool more, or in Windows type to display the file. The fact that the ls.txt is a regular text file also means we can access the data by opening the file and processing it in the usual way by using Python commands. So in this case, we simply looped over the lines and printed them, but we could have stored and used the data for some other purpose just as easily. It is worth noting that exposing a list of files in a text file like this is a potential security issue, and you should delete the file as soon as possible after processing it.